Hi everyone, so now we are going to start our new chapter which is logic families. A very easy topic, very straightforward. Now what do you mean by logic families? What do we study in this particular chapter? So in this chapter we will implement the logic gates using semiconductor devices. So whatever the logic gates that you have studied, AND gate, OR gate, NOT gate, XOR gate, NOR gate, NAND gate, all these gates can be implemented using some semiconductor devices. That means using diode you can implement this, using BJT you can implement this, using NMOS you can represent it, using PMOS, using CMOS circuit as well. So regarding the device physics of all this you study in EDC and analog electronics, device physics and amplifier. Here we are going to use it as a switch. As a switch means it will be either on or off. If it is on, that means logic 1. If it is on, that means logic 1. And if it is off, that means logic 0. That's it. On or off. We are going to use this as on or off. We will either apply 1 or 0. That's it. Nothing else. So this is what we are going to study in digital. So I will tell you about these devices. And most important thing is that we will implement all the devices using CMOS only. Okay. Because for gate guys, this is in the syllabus. In the syllabus, only CMOS is there. And 99.99% chances are there that in your interview as well, they will ask CMOS implementation only. They are not going to ask transistor level or any other thing. Okay, they are never going to ask TTL logic, ECL logic. They will only ask CMOS implementation. So in this video, we will see the implementation. In the next video, we will see the characteristics. Okay, so CMOS is the most important part that we are going to see. So we are going to implement all the logic gates using CMOS. What do you mean by CMOS? That we are going to see. Okay, so only CMOS implementation we are going to see, and this is what is mentioned in a gate syllabus. It is mentioned that logic gates and their CMOS implementation. Okay, so this is what we are going to see. So first device we are going to study, that is PMOS. So full form of PMOS is P-type metal oxide semiconductor. Now the depth of it, why it is called metal oxide semiconductor, what do you mean by metal here, what do you mean by oxide here, and which semiconductor will be there, so that you will study in EDC and analog electronics. Okay, and for placement guys, I will upload all these video in a placement course as well. Okay, but for gate guys, you can study this in EDC and analog electronics. This is out of the scope of digital electronics. But for placement guys, I will teach this subject right from the scratch. Okay, I will first teach semiconductor physics, then I will teach about this MOS physics, then we will study about CMOS. So placement guys, do not need to worry about that. But whatever that is required for digital electronics, that we are going to see. Okay, so this is your PMOS device. This is how it is represented, this way. Okay, you make this structure and this arrow is there, or this is the other way of representing. One more line you make and arrow is outward, and this is the third way of representing. This is what we are going to use in digital. This is the most important one. This is what we are going to use in digital. A simple bubble will be there. Now if applied input is 0 and if applied input is 1, how it will behave? So if applied input is 0, so there is a bubble, right? So if applied input is 0, then it will turn on. So it is like logic low. If applied input is 0, it will turn on, and there is this resistor connected. And if applied input is 1, it will turn off. So if it is turning off, that means it is open circuited. Okay, turning off means open circuited. Very simple thing. Let's go to NMOS. This is how NMOS is represented. In PMOS there was an arrow here, but here the arrow will be like this. And in PMOS the arrow was outward, but in NMOS the arrow is inward. It is known as N-type metal. Look, don't think much. Whatever that I am telling, that thing only you need to know for digital electronics. Okay, for digital electronics. In analog electronics and EDC you study in depth about it, right? Metal oxide semiconductor. Okay, so this is V in, this is V in. Now how it will behave? If 1 is applied, there is no bubble, simply it will be turning on. If it will be turning on, I think I should have made this structure better, right? I can make it something like this. If logic 1 is applied, what will happen? It will turn on. This is nothing but a simple resistor. Okay, if logic 1 is applied, it will turn on, so it will be shorted. And if logic 0 is applied, then it will be open circuited, right? So it is open circuited now, right? Well and good. Okay, let's move to the next slide. Now we need to see, forget about this if it is a NOT gate or not, just analyze this, what you are going to get. So V in, with respect to V in, I will write down my V naught. And what we need to apply, either 0 or 1. So if I apply 0 or if I apply 1, what will happen? If I apply 0, then what will happen? This is your NMOS. What is this? This is your NMOS. If I apply 0, this NMOS will be open circuited. If this is open circuited, then what will be your circuit? This will be your circuit, and this will be your V naught, this is your VD, and this is your RD. If applied input was 0, if applied input was 0, this will be open circuited. So this will be the circuit. Now VDD will come right here, right? VDD will directly travel and will come to V naught. So that means V naught will be 1. VDD is actually 1 and ground is actually 0. Okay. So VDD will travel because there is no current here. There is no current. Current is 0 ampere. So VDD will travel and V naught will be 1. If V in is equals to 1, then what will happen? If V in is equals to 1, then this MOS will be shorted. This MOS will be shorted, and here you are collecting V naught. This is your VDD and this is your R. So V naught will be equals to 0. So for 0 you are getting 1, for 1 you are getting 0. That means what is this? NOT gate. Right? Do the same thing for this guy as well. If V in is 0, what will happen? This will turn on. If V in is 0, this will turn on. So what will happen? This is your VDD. If this turns on, then it can be replaced with the resistor. Sorry. If it turns on, it will be shorted. And this will be your RD. And this is your V naught. So VDD is directly exposed to V naught. So you are getting 1. And if V in is 1, then if V in is 1, if V in is 1, then it will be open circuited. This will be open circuited. This is your RD and this is your V naught and this is VDD. If it is open circuited, so this will drive 0 ampere current. If this is driving 0 ampere current, then V naught will be what? 0. Basically, this is driving 0 ampere current. So RD into 0 will be what? 0 only. So V naught will be 0. So what you are getting? This is also NOT gate. Very easy thing, right? Very, very straightforward. If you apply 0 here, what will happen? This will turn off. So VDD will come. If you apply 1, this will turn on. So 0 will go there. Same goes for this. If you apply 0, then what will happen? This will turn on. So VDD comes here. And if you apply 1, this will be off. Then this 0 goes there. That's it. Okay. Forget about the name. Whatever that is written, forget about that. Let's make our table now. If A is 0 and B is 0, that means both are off. If both are off, that means both are open circuited. If both are open circuited, so what will happen? There will be 0 current here. If there is 0 current here, that means this VDD will directly come here. So V naught will be equals to 1. If both are 0, that means both are open circuited. So VDD will directly come. 1 is 0 and 1 is 1. If 1 is 0, that means A is 0, then this will be open circuited. यार ये कभी टिकता ही नहीं है, स्टाइलस कभी नहीं टिकता भाई. If A is 0 and B is 1, if B is 1, that means this will be shorted. And here you are collecting your V naught. Now from upper side there is this RD connected and this is your VDD, right? But this 0 is directly going here, no? This 0 is directly going here. So V naught will be equals to 0 only. Are you getting this point? And if A is 1 and B is 0, that means A will be shorted. If A is shorted, so 0 is going here. And if both are 1, that means both are shorted. So this is also delivering 0, this is also delivering 0. So 0 will be coming here. So what you are getting, which kind of gate is that? Yeah, I should remove it. Which kind of gate is that? This is A plus B bar, which is NOR gate only, right? What about this? If A is 0 and B is 0, that means both are on. A is 0, B is 0, both are on. Simply it will be a wire. And then there is a R and this is connected to V naught. If both are on, simply it will be a wire. So V naught will be equals to VDD, right? If A is 0 and B is 1, A is 0, that means A is on, A is on, but B is 1, so B is off now. So that means that will be open circuited. Now this is the resistance R. So what you are going to get here? V naught equals to 0. Same goes for the other one. If A is 1 and B is 0. Okay, I took the other case here. Actually, I solved this case that my A was 0. That means that was on. A was 0. A is 0. That means A is on, and B is 1. That means B is off. So that was the case here. So we got 0. Now A is 1. That means A is off now, and B is 1. So B is there. So again the same case is there. Again there is no current. Again there is no current. So what will happen? 0 current will flow, and V naught will be 0 only. Here 0 current will flow. This is open circuited. Upper part is open circuited. From here 0 current is flowing. So V naught will be equal to 0. If both are not open, if both are open circuited, that means if both are not on. If both are not on, what will happen? This will also be open circuited. This will also be open circuited. That means there will be no current. If there is no current, that means across the resistor there will be 0 current. If there is 0 current across the resistor, that means V naught is equal to 0. Are you getting this point? Very simple. So this is also your NOR gate only. What did you understand from here? If two NMOSs are in parallel, this is what we call parallel. If two NMOSs are in parallel, just add them up. Since they are connected to ground, they will deliver ground. So use a bar. Basically, if I add them, if two are in parallel, what I can do? I can make one MOS there. One NMOS I can make, and at the input I can apply A plus B. So this is how I can reduce my circuit. This is how I can reduce my circuit. If both are in parallel, then what I can do? I can just add them up. So this is how I will be reducing the circuit. Now one thing I know, if this is my circuit, then at V naught I just receive the bar of it. Better I put A here. Okay. If I put A here, so at V naught I will receive the bar of it. V naught is equals to A bar in both of the cases. So here A plus B is applied, so at V naught what I will receive? At V naught you will receive A plus B bar. Now can I call this input as A bar? If I replace this as my NMOS, so can I call this thing that my applied input is A bar? Do you agree to this point? A and there is a bubble. So if I take bubble out, so A will be becoming A bar, right? And my B can become B bar, and this is my VDD. Right? So what is my Y equals to? A bar dot B bar. Okay, parallel connection we will see. Parallel connection we are going to see. So V naught is equals to A bar dot B bar. Tell me one thing, if both are on, if A bar is also on, that means if A bar is 1 and B bar is 1, then what will be delivered at the output? A bar is 1, A bar is 1 and B bar is 1. That means at the NMOS you are having 1 1. So what will be delivered at the output? VDD. So V naught will be 1. Basically if A bar is 1 and B bar is 1, then V naught will be equals to VDD. So here another bar I am not gonna put. If both are 1, you are getting VDD at the output. So my V naught is actually A bar dot B bar. Either you can solve by this, okay, or you can think it as a NMOS only. A bar, B bar. So my V naught is equals to A bar dot B bar. If it was connected to ground, then it would have delivered bar. So basically if it is A plus B, so what I would have written? V naught equals to A plus B. Then I saw that it is connected to ground, bar. Then what I would see? If they are connected in series, then I will multiply them. A bar dot B bar. And since they are connected to VDD, so I am not going to put any bar there. Are you getting this point? So A bar dot B bar is equals to A plus B bar only. So if they are connected to VDD, I am not going to put any bar. If they are connected to ground, I will put a bar. Okay, let's solve this. So what will be your V naught? I told you one thing, in a series they will be multiplied, A dot B, and since they are connected to ground, I will put a bar, or otherwise forget about it, I will just solve it here. Both are 0 0, that means both will be open circuited. Both will be open circuited, that means VDD will directly travel here, it will be 1, right? If 1 is 0, 1 is 1, that means this will be open circuited, so certainly there will be no current, because to flow the current all should be on. If this is gone, if this is open circuited, so there will be no current, so again VDD will come to V out. Same goes for the next case, this is on, this is off, so again VDD will come to V out. If both are 1, that means complete this will be shorted, complete circuit will be shorted. If both are 1, complete circuit will be shorted, so V naught will go to 0. So what do you think, what is your V naught? A dot B bar. Say yes or no? It is A dot B bar. What about this? What did I tell you? What I can do? I will solve it by this method as well, but if both are connected in parallel, I can add them up. But there is a bubble. So A bar plus B bar. Now will I put a bar here or not? That will depend on where it is coming from. It is coming to VDD. It is coming from VDD. So I am not going to put any bar. So yes, this is my final answer. So what I am getting? A B bar. A bar plus B bar, they are not connected to ground, they are connected to VDD. So not any bar there. A dot B, since they are in series, so A dot B, but they are connected to ground, so bar would be there. Or let's solve by this method. If both are 0 0, that means both are on. If both are on, that means VDD will be directly supplied here. If both are on, VDD will be directly supplied here. If A is 0 and B is 1, if A is 0, that means this will turn on and this will be off. If this turns on, that means VDD will be supplied here. And if this turns on, then VDD will be supplied here. If both are off, then VDD will not be supplied. If both are 1 1, if A and B both are 1 1, that means both are off. If both are off, that means 0 current will be there. So across the resistance, if there is 0 current, so V naught will be 0. So what is your V naught? AB bar. There you go. Okay. So this is how we can write it, or this is your AB bar only. We will write down the conclusion, but yeah, one more thing we are going to see. So this resistor we are using now, this resistor. So actually we never make this, we can never use resistor R there, because resistor R will depend on temperature. These kind of resistor will highly depend on temperature, and they can change very quickly with respect to temperature on your IC. So you will make these resistors from your MOS only. So you can make this resistor from PMOS. Okay, so resistance R is there, this is your VDD supply, resistance R is there, and then there will be a network. So these kind of things we have already seen in analog electronics, how to make these resistors. Just I am telling that in your digital electronics as well, if some question is coming and where they are showing that from, if you are looking from here, you are getting to see R resistance. So if they make any circuit like this, that if they are making any circuit like this, or they might not give this this as well, okay, or if they are giving this, and then there is some network, and here you are collecting some output. So don't get confused, just you need to see there will be some resistance R from here. It would be equals to 1 by GM, but that is out of the scope of digital electronics. But from here downward, this is a resistance only. So if you see anything like this, that means you need to consider that as a resistance. Okay, so this can also be seen in some of the questions, that there will be some here some NMOS network, and in place of this R they will be using this MOS. Okay, so that can also happen. So now what is the conclusion? If MOS is connected like this, so V naught will be my A bar. Okay, if both are in parallel, sorry, if both are in series, so A into B, and since they are coming from ground, so bar. If both are in parallel, so A plus B coming from ground, bar, and this can be replaced as something like this, A bar. This bubble can travel and it can be replaced by this. Although you will never have to use it, let me tell you, you will never ever have to use this kind of analysis, because in actual we are never going to implement any logic gate the way we implemented. We implemented the logic gate like this, right? Using NMOS only or using PMOS only. But we implement all the logic gates using CMOS. So what is the reason behind it? So I will just tell in a line. If it is asked in your gate examination, then you should be able to tell. The reason is CMOS have zero static power dissipation. CMOS has zero static power dissipation, and NMOS and PMOS will have finite static power dissipation. That's the reason why we are going to use CMOS. In CMOS, what will happen? We will have NMOS as well and PMOS as well. And what do you mean by static power dissipation? What is dynamic power dissipation? That is out of the scope of our course. Still, I will add these videos to my gate guys as well. To the gate students as well, I will add these videos. But you can skip it if you are not having much time. Because CMOS VLSI will take 6 to 7 hours to study. Okay, at least 6 to 7 hours you will require. So if you are not having time, you can skip that part, because there is 0.1% chance is there that they can ask this question, because it is not mentioned in the syllabus. But still CMOS implementation is mentioned, then it's my responsibility that I will add CMOS inverter videos. Okay, we will completely study CMOS right from the scratch. It is very necessary for the placement, guys. It is very important for the placements, but gate aspirants can ignore it. Just for the fact, just for the information I am telling, why we don't use these guys? We have implemented NAND gate. So if I ever need to implement NAND gate in my design, I am not going to use this circuitry. I am going to use CMOS. In CMOS, what will happen? This downward will be same, okay, and this upward will be this. Basically, in CMOS, what will happen? Here there will be PMOS circuit, and here there will be NMOS circuit, and this will be my output. This will be my V0, and here will be VDD. So in place of this resistor, you will replace this circuit. That's it, nothing else. So at a time, only one device is on. At a time, one device gets on. Both devices will never turn on. Basically, it will never happen that PMOS is also on and NMOS is also on. Only at switching threshold it will turn on. You are not going to understand anything. I am just adding these points. So just don't get confused. This is a very deep CMOS VLSI. Will not be useful for you. Okay. But I will add the video. So only at this point it will turn on. So there will be a high power consumption. Otherwise, there will be only dynamic power consumption. When it is static, at this point there will be no power consumption. But in this case, there will be power consumptions. In PMOS and NMOS, there will be power consumption, because there will be a time when this will be on, but it will be of no use. Okay, we will see it. We will see it in CMOS VLSI. I will add the videos. No need to worry. If you want to study, then you can study. Otherwise, or in the gate examination, these kind of questions only will be asked. Whatever that we are covering in this lecture or in the next lecture, only these kind of questions can be asked in gate examination. Okay. Yeah. Now, if this question is coming, the given circuit represent which logic circuit? So what will be your answer? How will you solve it? What you can see here, first you can calculate the output here. There are two methods actually. First, you can make the truth table A, B and V0, or in place of that Y can also be written. So A, B, V0. So 0, 0, 0, 1, 1, 0 and 1, 1. So A and B, if both are 0, what will happen? Both will be off. If both will be off, then VDD will go here. If both will be off, then what will happen? This VDD will go here. Actually, input current of MOS is always 0. So if this current is 0, they are not driving any current. So 0 current is flowing through RD as well. So this VDD will directly go here. VDD means high. If it is high, that means output will be low. If this input is 1, that means it is shorted. If it is shorted, that means output will be 0. Are you getting this point? Now, in the next case, what will happen? A is 0, that means it is open circuited. B is 1, that means this is shorted. This is shorted. If this is shorted, that means 0 will travel here. So if this is 0, this will be 1. Because 0 means it will be open circuited. If it is open circuited, then VDD will directly travel here. So this will be 1. Same goes for the next case. And if both are 1, that means both are on. If both are on, then what will happen? 0 will travel here and the same case will be there. If both are 1, that means both are on. If both are on, that means 0 will travel here. And if this is 0, then at V0 what you will have? 1. Because 0 means this is open circuited. If this is open circuited, that means VDD will come. So this is the one way of writing it. And what did you get to know? What is this? So V naught is equals to A plus B, right? Your V naught is A plus B. This is the truth table of OR gate. What is the other way? What you can see, both are in parallel. That means what it will give me, A plus B, and since it is connected to ground, A plus B bar. Now there is a NMOS. To the input, what do you see? A plus B bar. This is your VDD. This is your RD. So at output, what you will receive? Bar of this. A plus B bar and another bar. So A plus B. That's it. You don't need to make truth table. Okay, you are not going to make truth table. If 7 to 8 inputs are coming, then what you will do? You are not going to make truth table. So there you need to see parallel and series connection. So that's why I wrote that conclusion. This will be used everywhere. Okay. So what did I tell you? We will implement all the circuit using CMOS. So this is our CMOS implementation. There will be inputs as well. Here there will be input. It will also have some input. Now this is known as pull up network. Okay, pull up network. It pulls up the output. If you connect a cap here, that means it will charge this cap, and this is known as pull down. When you study CMOS inverter, you will understand it. Pull down means it will just discharge it. Just for the information, I am telling these things. Okay, just for the information, because if it is asked in 1 mark in true or false, which is very rare, if it is asked, then still you will be able to answer it. Okay, and I will add the video. Do not worry about that. If you have time, then you can study it. But what can be asked? Why CMOS? Almost zero static power dissipation. I am writing why CMOS, static power dissipation. Great noise margin. What do you mean by noise margin? We will study in the next lecture. Even gate guys will study it. Okay, great noise margin. It has a great noise margin. How to calculate the noise margin, that you are not going to study. How to calculate the noise margin of a CMOS, so that placement guys will study, but gate guys have to restrict themselves that this much is not required. If you are someone preparing for gate 2026 or 2027, you are having more than a year, then it is fine, but gate 2025 is very near. So if you are studying for gate 25, just do the things which are more important for you. More important, or I would say, like, asking of all these things, there is a 0.2% chance. Okay, I am telling you 0.2% chance that they will ask all these things. They will only, what they will give is that they will give the circuit and they will ask you what does it represent, like this question. These kind of questions they can ask in gate examination. But for placement guys, we cannot take risk. The interviewer can ask anything. So for them we will cover everything. But here I am just telling, if in 1 mark, in worst case it is coming, then also you will be able to tell, right? Let's go to the next one. Now it is a NOT gate. How it is a NOT gate? So what you need to see in the implementation of CMOS logic, what you need to see here, I should have made it better. Basically, whatever the circuit that is represented below, the same kind of circuit will be represented above as well. Okay. If I look from the down, what I will say, that V naught is equals to A bar directly. And if I look from the up, this A can be replaced with A bar as well, right? A can be replaced with A bar as well. So A bar will come, but will be connected to 1. So I am not going to put another bar. Here, what I can say, A will come, but it is connected to ground, so I will put bar. Plus, or what is the other possibility? A bar would come, since there is a bubble, so I can call it as A bar. A bar would come, but it is connected to VDD. So I am not going to put any bar. So A bar plus A bar is equals to what? A bar only. Basically, whatever the network you see downward, the same network you will see upward. Right? Now, let me show you another observation. When we implemented the same thing using series of NMOS, what we were doing? Parallel of PMOS. When we are doing parallel of NMOS, we were doing series of PMOS, right? Parallel, series parallel, right? Now in the examination, in the interviews, this question is only for the interviews. In interviews they can ask you, implement NOR gate using CMOS implementation, using CMOS logic. Using CMOS logic, implement NOR gate. So what you are gonna do? Even in the, when you go to M.tech interviews after gate, these kind of questions are very, very famous. You need to implement NOR gate. So what you are gonna do? Y is equals to NOR gate. First you will write down the expression A plus B bar. Here you can see plus. So in case of NMOS, when plus will come? When both are parallel. Plus will come when both are parallel, and when both are in series, multiply will come. So in case of NMOS, this should be the scene. So this will be your A plus B, and since they will be connected to ground, always NMOS will be connected to ground, and since they will be connected to ground, bar will come on its own. So A plus B bar. Here you can connect a resistor, but now we are not going to connect a resistor, we are going to connect what? PMOS logic. So if they are in parallel, that means PMOS logic will be in series. So this is how you will implement. So what is the step of implementing? Did you understand this point? This you can tell VDD, A, B, anywhere you can show, upward or downward, that doesn't matter. So what is the step? You will first write down the expression. You see the plus there. If that is the plus, that means A and B will be in parallel. And one thing you know, that bar will come. Bar will come on its own, because A plus B, since they are connected to ground, bar will come. So that you already know. If you already know that, then you do not need to care about that bar. And once you have implemented this, you just need to take the other of that. Then if they are, that means if they are in parallel, this will be in series. Well and good. Let's go to the next one. Implement XOR gate using CMOS logic. So this is the expression of XOR gate that we know. A bar into B plus AB bar. And they are saying use only one stage. You only have to use one stage. That means in one stage only, basically, pull up network will be there, pull down network will be there, and this will be your output, this will be your ground, this will be your supply. So in one network only you need to tell. You cannot use another stage here. Okay, you cannot use any other stage. So this is what they are asking, use only one stage. So using what? Using my NMOS logic I can implement it. Using NMOS logic I can implement it, but what is the catch? That if I use NMOS logic, whatever the design I do, then at the output bar will come, because it is connected to ground. So what I need to do? I need to take double bar here, right? A bar B plus AB bar. If I take double bar, this expression remains the same. Now what is the bar of A bar B plus AB bar? Basically it is A XOR B double bar I am taking. And what is this? A XOR B bar. And how I can represent A XOR B? That is A bar B bar plus AB. And then there is a bar. So what I need to implement? A bar B bar plus AB bar. A bar B bar, that means they are in series. If they are in multiplication, that means they are in series. Both are in series. A and B both are in, A bar and B bar both are in series. A bar and B bar both are in series. They should tell that A bar and B bar are available. A bar B bar available. Okay. Otherwise for this as well you need to use another implementation. Basically to make A bar and B bar, you will have to use this configuration. That you apply A here and you get A bar. To you apply B here, you get B bar. But they will say that this is available. Then I can implement this in one stage only. Now what is the other thing? Other thing is A into B. Again you need multiplication, so you need series. A into B. Now you need addition. Addition means both should be in parallel. There you go. Both are in parallel. Both are in parallel. You need both of them to be in parallel. A into B, A bar dot B bar. Addition, both are in parallel. And since it is connected to ground, bar will come. So what will come here? A bar B bar plus AB and then bar. But the thing is what? You need to make our PMOS logic as well. How will you make PMOS logic? What did you see here? A bar and B bar are in series. That means A bar and B bar will be in parallel. A bar and B bar will be in parallel. What else did you see? That A and B are in series. A and B are in series, so they will be in parallel. A and B will also be in parallel. So they are also in parallel. What did you see then? This configuration and this configuration. This configuration is represented by this. This configuration is represented by this. Both are in parallel. That means they will be in series. Are you getting this point? Did you understand this point? I made these two combination in series. Let me show it once again. Where to where I am going? Implementing this is easy. What I need to do now? I need to implement the PMOS logic for the same. A bar and B bar are in series, I will make them in parallel. AB in series, I will make them in parallel. Now this configuration and this configuration, they are in parallel. That means this configuration and this configuration will be in series. So there you go. Now if you need to analyze it, you will not even look here. I am more comfortable with NMOS, I will just look down. I will be able to solve it. Well and good. Let's go to the next one. You need to implement 2 cross 1 mux. What is 2 cross 1 mux? This is S 0 1 I am showing. This is your I0, this is your I1, this is your Y. So what will be your Y? Y will be equals to S I1 plus S bar into I0. Now they are saying you can use 2 stages. You can use 2 stages, that means the other stage I will use as inverter. I know that using NMOS I will get a bar here. I will get some expression X and then bar. To get the expression X, what I can do? I can use inverter. So inverter, how can I implement? Inverter I can implement very easily. What is the schematic of inverter? Here your PMOS will be there and downward your NMOS will be there. Inverter you should keep in mind, okay? That is very simple. There you are not going to think anything. PMOS and NMOS, both input connected together. PMOS and NMOS, both input connected together. Okay, so there you are not going to think anything. Inverter you should use. So using 2 stages means, that means next stage will be inverter. So Si1 plus S0, S bar I0. So this you should implement on your own. S into I1, S into I1, that means S and I1 will be in series. Now S bar I0, S bar and I0 will be in series. And then both are added, so both will be in parallel. Okay, did I show the ground here? Yeah. Or you can connect together, show the ground, or you can connect like this as well. So now both will be in parallel since there is a addition. Now I just need to make the same kind of diagram is there, right? I need to make the PMOS logic as well. So this is the PMOS logic I am drawing. This is VDD. Okay, so SI1, and this is my output SI1 and S bar I0, right? S bar I0. Both are in parallel. If both those are in parallel, they are in series. So this is not your final output. What is this output? If I call this as X, if I call this as X, so what is my X? X is S into I1 plus S bar into I0. Since it is connected to ground, bar will come, right? So if this is the scene, that means here what we need to use? We need to use inverter. So how do we implement an inverter? So for that we don't need to think much. Simply I know one thing. this is how the inverters look like. Here the input should come, yeah. These kind of basic question they can ask either in analog design interview as well, in a digital design interview as well. These kind of questions are asked in analog design interview as well. Okay, so this is your X, which is this, and this is your final V naught. Okay, right? So this is the proper design. Now implement this AB plus C plus D into E. So AB, A into B. Then C plus D into E. So E is multiplication, E is in multiplication with something. What is that? C plus D. That is C plus D. This is C and this is D. C plus D in multiplication to E. A into B, and both are in addition, so both are in parallel. Are you getting this point? C plus D into E plus A into B. That's it, right? And above you need to make your PMOS logic, so that you can make, I am just using a resistor. You can make the PMOS logic on your own. How will you make it? A and B in what? A and B in parallel, in series with C and D in series parallel to E. A and B in parallel in series with C and D in series parallel to E. Okay, a rough diagram I am drawing. A, B in parallel, AB in parallel, in series with what? These two are in series, that means this should be in parallel. So E here, and these two are in parallel, that means these two should be in series. So this will be the diagram, right? So this you can think on your own. So fairly we are not drawing it. Now for the gate aspirants, this circuit will be given and they will ask you what is this. Wait a second. This is not the final answer. We will use an inverter here as well, right? I forgot to use the inverter because this will give us a bar, right? This will give us a bar. So here I will have to use an inverter. This will be the final output. Okay, so inverter will also be used so that whatever the expression that you are having, that will take another bar. So here you are having Y bar actually, and then V naught will be equals to Y. Okay, then let's see some questions. What this represent? V naught is equals to what? A plus B into C parallel to plus D, and then there is a bar. Don't forget this bar ever. A plus B into C plus D and then bar. This is your V naught. फिर टेढ़ा चल रहा है यार पेन, है ना? Now this question, this is a different kind of problem. You can either make the truth table or you can think. How will you think? Or you can solve it by options as well. Tell me one thing. If B is equals to C is equals to 1, then what will be your Y? A. If B is 1, C is 1, that means this MOS is on, this MOS is also on, A will be delivered to Y. In which option you get this thing? If B and C are 1, if B and C are 1, this is becoming, if B is equals to 1 and C is equals to 1, so A plus 1 will be 1 only. This is becoming 1. This option is wrong. Okay. In the next one, if B is 1, A is there as it is, and C is equals to 1, so it would be 0. So this is becoming equals to A. So this is our possibility. If C is 1, A, B is 0. So this is also a possibility. And this is also a possibility. So one option only I could eradicate. Other thing I can see, if C is 0, if C is 0, then Y will be equals to B. Do you agree to this point? If C is 0, then Y will be equals to G. Because if C is 0, this will be on. If this is on, then Y will be equals to B. So let's see it. If C is 0, A is don't care here. A is don't care. A did not even come in action. So if C is 0, then what will happen? Y will be equals to A plus 0. If we put here, it would be 1. So A plus 1 is 1. So answer is B. So this is one of our possibility. I am just putting C is equals to 0. That's it. If I put C equals to 0 in this one, what I will get? A into B plus 1. Answer is A. No, our answer is B. So this is wrong. What I am going to put C equals to 0 here. If I put C equals to 0, this expression will also be 0. So this is also wrong. So which is the correct option? Correct option is this. I just wrote down the condition. B equals to C equals to 1, Y will be equals to A. So put B equals to C equals to 1 and see if you are getting the correct answer. Put C equals to 0, Y will be equals to B. C equals to 0, Y will be equals to C. Put here. Or how you can write? Y is equal to the same thing I am going to write. If B and C are there, then my output will be A. Or if you have studied combination circuit, this is how we write down the output. If B is there and C is there, then my output will be A. Or if C is not there, that means if C is 0, if C is not there, then my output will be B. There you go. And now you can simplify it. So that would be B into AC plus C bar. And that can be replaced with B into A plus C bar. A plus C bar. B into A plus C bar. So this was your method 2. Okay. Method 1. In the examination, I will better go with this method. If B is there and C is there, then A will be delivered. Plus, if C is not there, then B will be delivered. There you go. Okay. This was a good question. Write down the expression of this. So F will be equal to what? A into B plus C. In parallel, that means plus D into E. Don't forget the bar. A into B plus C plus D into E. Don't forget the bar. The same thing that we saw in MOS can be seen in BJT as well. The same goes here. The same goes here. If Vin is equals to 1, it doesn't look like MOS. Does not it look like NMOS? This looks like NMOS only, no? Doesn't it look like NMOS? It looks like NMOS only. NMOS was this. This was the arrow. So this is like NMOS only. You can treat this as a NMOS. Always treat this. What is this? This is NPN. You are going to study all this in your analog electronics course. So this is your NPN. NPN. Okay. So this is your BJT only. So BJT, NPN BJT works same as NMOS. So if Vin is 1, that means it will be on. If it is on, then V0 will be 0. And here I should connect VDD, not VDD. In case of BJT, we use VCC, collector voltage. It is a supply, it can be shown by anything, but generally we shown it VCC. And if Vin is 0, this will be off. So VCC will be directly traveling here. So it will be off and V0 will be equals to 1. Okay. So just treat this as a NMOS only, nothing else. So what will be your output expression in terms of X, Y and Z? So first tell me what you are gonna get here. I am calling this as P potential. Potential P will be a bit different. Let's call it VA potential. Again, this will also drive almost 0 ampere current. So forget about this current. So what will be your VA potential? VA minus X by R plus VA minus R, क्या कर रहा हूँ यार मैं, VA minus Y by R plus VA minus Z by R is equals to 0. So 3VA is equals to X plus Y plus Z, right? So VA is equals to X plus Y plus Z by 3. So basically here there is no meaning of 3. In case of digital there is no meaning of 3. Basically here you are getting the addition of these 3 Boolean logic. So VA, what I am going to say is that this represent the addition of these three Boolean logic x plus y plus z. And if at BJT, just consider this as a NMOS, okay? Just consider this as NMOS. If this is your x plus y plus z, what you are going to receive at V0? Simply the bar of that, x plus y plus z bar, okay? Just the bar of that. So this is your final answer. This is your x plus y plus z. Although you are having here x plus y plus z by 3, right? 3 VA is equals to x plus y plus z, but there is no meaning of 3 here. Basically, you will just receive the bar of that. Solve this question. If you know diode circuit, then you will be able to solve it. If you know diode circuit, so knowledge of diode circuit is required here. How you are going to solve it? Make the truth table, okay? So make the truth table. In case of diode, always make the truth table. Do not worry about making truth table, because in case of diode, you cannot go with any shortcut. These kind of questions we have already solved in analog electronics, but here also let's solve it. I will apply open circuit test. Both I will consider open circuited, okay? Now I will see what will happen. This 5 will come here. So this node is at 5 volt and this node is at A and B. So if A and B both are 0, so in case of diode, I hope you know this thing. This is known as P, this is known as N. P is at higher potential and N is at lower potential. This is 0 and this is 5. P is at higher potential. Then what will happen? Diode will turn on. If diode turns on, then A will travel here, B will also travel, which is equals to 0. So V0 will be equals to 0. If diode turns on, then 0 will travel here, right? In the next case, 0, 1. If A is 0 and B is 1, so this will be off, because across the diode, B is 1, that means 5 volt only. This is also 5 volt, this is also 5 volt. So this is unbiased. So this will be off, but this is on. So 0 will travel here again. 0 will travel here again. And 1, 0, this time this 0 will travel here. But if both are 1, 1, then both are off now. Both are off now. If both are 1, 1, both are off now. Then what will happen? This 5 will travel here. Are you getting this point? Although you will understand this in initial lecture of a diode circuit, okay? In first or second lecture only, we study these things. Open circuit test, short circuit test. So what is your V0? AB. Let's solve this question. What do you see? Which circuit is that? AB. In the examination, if this question is coming, first you will solve this stage. You will get to know it is AB. The same kind of stage is this. This is A into B. This is AB into C. Here you are getting AB into C. And what is this? Inverter. So A into B into C bar. AB, C. This is the same stage only, no? This stage and this stage are same. So AB into C, ABC and then bar, right? Solve this using PMOS using NMOS only. Consider this as an NMOS only, right? V1, V2, V1 plus V2, here what you are going to get? V1 plus V2 bar, right? V1 plus V2 bar, both are in parallel. So V1 plus V2, but they are coming from ground, so bar. And what will you receive from this? Bar of V1 plus V2. V1 plus V2 bar and then another bar, because this is your inverter only. So what you are going to get? V1 plus V2. There is very rare chance that they will ask these questions, because this has been removed from the syllabus. But still they have written CMOS implementation, so why should we drop anything? So we are using this logic gate as well. This logic implementation as well. Now you need to tell the expression of Z. This is a good question. Okay, try it on your own. What we need to do? Make the make the truth table here, because if you go without truth table, you will not be able to solve, because here there are two type of devices, no? BJT and diode, both are there. So make the truth table. Whenever you get confused, make the truth table. So X and Y two inputs are there and Z will be implemented. 0, 0, 0, 1, 1, 0, 1, 0 and 1, 1. If this is 0, this is off, right? If this is 0, this is off. If this is off, then what will happen? This VCC will travel. Basically, there is 0 current here. If there is 0 current here, that means 0 current will be there from this guy as well. Are you getting this point? With diode, what you are going to do? With diode, you are going to apply open circuit test. This is diode is my open circuited. Here you are having Y. Diode is open circuited. Here you are having VCC, which is connected to R. This is your Z. This is your Z. Now, if you applied X equals to 0, that means this is open circuited. If this is open circuited, then there is no current through this R. VCC will travel here. Now, across the diode, what do you see? Here you are having VCC, and here you are having 0. So what will happen? Diode turns on. Diode is on. At P you are having VCC, and at N you are having 0. Diode turns on. If diode turns on, then what will happen? This 0 will travel upward. This 0 will travel upward, Z will be 0. Again, let's see it again. X is 0, this is open circuited. Across diode, I will always apply open circuit test. That means I will see the potential here and here, across P and N. Then I go to know that VCC travels here. So across P I am having VCC, across N I am having 0. That means diode is actually turning on. I applied open circuit test, but I got to know that diode is actually turning on. That means this Y will travel here. So if X is 0, Y will travel here. Are you getting this point? So in this case, it will be 1. Why is that so? If X is 0, this will be open circuit only. VCC will again travel here. Now, Y is also 1, so this is also VCC. Now you can assume that this is my diode. So both are having the same potential. So I will say that diode is off. If diode is off, what will happen? This VCC will remain there as it is. If diode is off, then VCC traveled here. So this diode is open circuited only. If diode is off, that means it is open circuited only. So if it is open circuited, that means VCC will travel here. So this will be 1, right? Let's see the next condition. In the next condition, BJT is on now. If BJT is on, so there is no one that can stop Z to be 0. If BJT is on, then certainly Z will be 0. If BJT is on, there is no one that can stop Z to be 0, because if BJT is on, that will be short circuited. If this is short circuited, then 0 will travel here. That's it. So this is the truth table. So what you are going to get? Z equals to X bar Y. Are you getting this point? So when BJT is on, when X is 1, then this path will be shorted. So Z will be certainly 0. Whether diode turns on or off doesn't matter. Diode will turn on or off, that doesn't matter. This will always be 0. There is no one who can stop it. So now this node will be 0. Now even if you apply 5 here or you apply 0 here, diode will always be off. So when it is 1, you don't need to care. When it was 0, it was open circuited. This VCC bar coming here. Then we need to see the operating condition of diode. Well and good. From there we go to know this expression. Let's see the next question. This is a very good question. We will solve it. But the next one is transmission gate. So yeah, let's solve it. You need to find the expression of Y. Try it on your own once. Okay. When I saw this question first, I was also not able to get the correct option, match the correct option, but I was able to get the answer. So how we will solve it? Y expression we need to find. One thing I know that it is coming from the ground. Right? Coming from the ground. So certainly bar will be there. So what I can do, can I write Y as X bar? My target is to find the expression X. Right? Or just forget this thing. What I know that if I turn them on, if I turn them off, if I turn these switches on, if I turn them on, then my Y is going towards 0 only. If my Y if this circuit gets short circuit path here, that means Y will be 0. So when Y can be 0? Are you getting this point? What I am doing? I am checking when my Y can be 0. If I get to know when my Y can be 0, what I can do? Simply I can put bar on that. That will be my expression. Are you getting this point? Basically, if A is on, B is on and C is on, if these three are on, that means certainly Y will be 0. So if A is 1, B is 1 and C is 1, then Y will be 0. Or if A is 1, D is 1 and F is 1, then Y will be 0. Or if E is 1, D is 1, B is 1 and C is 1, E, D, B, C, then Y will be 0. G, D, B, C, G, D, B, C, or EF or GF, which we don't have. ABC, ADF, EDBC, GDBC, EF, GF. All these will make Y equals to 0. So a bar I need to put. For this you wrote, for this expression, what did you wrote? Your V naught or Y. You know that A and B are on, then it will make your Y equals to 0. So then you put a bar. Same thing we are doing here. If my A, B and C are on, or A, D, F are on, or E, D, B, C are on, or E, D, B, C, or E, F are on, or G or F are on, then I will get a short circuit path. Short circuit path here you are getting, short circuit path here you are getting. This is your short circuit path. This is your short circuit path. This is your short circuit path, right? Just I need to see short circuit path. If I am getting short circuit path, then Y could be 0, and then just I need to put a bar. So that is my final answer. There you go. Are you getting this point? Related with AB, or you can relate with this as well. Basically, here also you did the same thing. A plus B, you know when it will turn on. Either A is on or B is on, but you know it will be going to ground, so there is a bar. So I know my Y is going to ground, so I will put a bar there. That's it. Okay. Let's see this question. Just solve it as a question, then I will tell you which circuitry is that. Don't get confused with this circuitry, okay? This is nothing but PMOS. So sometimes it is shown by this as well. This is your PMOS. This is your PMOS. And then lower one is your NMOS. So don't get confused with that. Wait a second, what I am doing. Yeah. So this is your PMOS and this is your NMOS. Just a way of representing is different. Okay, NMOS, PMOS. So you know this thing, this S is there, and here S bar is there. Here S is there. So how will you write Y? How will I write Y? Let's talk about this guy. If S is 0, then I naught will come. If S is 0, then I naught will come to Y. Or if S bar is 1, that means if S is 0, or you can say if S bar is 1, then I naught will come to Y. Or if S bar is 0, that means I will write S bar is 0. If S is 0, that means I will write S bar. If S bar is 0, that means I will write S, right? So if S bar is 0, then I1 will come to the output. Or if S is 1, then I1 will come to the output. If S is 1, then I1 will come to the output, right? So what is your Y? S bar I naught plus S I1. What is this? 2:1 mux. Now this circuitry that we used here, this is known as transmission gate, okay? And I will call this is known as transmission gate because in transmission gate at PMOS and NMOS complementary logics are applied, okay? Complementary logics are applied. So this is your what? Transmission gate. Did I say transmission logic? No, it is known as transmission gate. Okay, this is transmission gate. This particular circuit, this is also a circuitry. So this is your transmission gate. Now there are a lot of way of representing it. This will be your input, this will be your output. Always complementary logic will be applied. Here A, here A bar. Here A bar can also be there, here A will be there. In this case you saw that S bar was there, this was S. So anything could be there, okay? So A bar. This is the another way of representing it. This is another way of representing it. They show it like this, okay? अरे यार ये ऐसे So when you study static timing analysis in a deeper manner, you will see transmission gate are represented like this. So what will you understand here? That if A bar is, what will be the output here? If you want to write down the output, what will be the output? If A bar is 0, then input will come. If A bar is 0, that means another bar. So I will put A only, then input will come. Or if A is 1, then input will come. So both does the same thing. So A into input and A into input will be A into input only. For all the diagram, if C is 1, then input will come. If C bar is 0, that means if C is 1, then input will come. A bar is 0, that means if A is 1, A bar is 0, that shows if A is 1. So if A is 1, input will come. If A is 1, input will come. Those who have studied combination circuit, they are able to understand this thing, right? What I am saying. If A is 1, input will come. A bar is 0. Or you can say if A is 1, then input will come. So both are doing the same thing only. Why they are used then? I could have only used PMOS. Why I am using NMOS? Or I could have only used NMOS. Why I am using PMOS? For the power dissipation purpose. We will understand these things, but not relevant to gate examination. So you will always use complementary logic. That means P as well and N as well. So that static power dissipation is 0. Okay, so that we will understand. No need to worry about that. Right? Okay. Now, how this circuit will work? So here you can see enable button as well and D button as well. So let's see how this, what will happen. If enable equals to 0, what will happen? If enable is 0, if this is 0, then this will be 1. If enable is 0, this will be 0, this will be 1. 1 nor anything will be 0. That means D plus 1 will be 1 only. 1 and then bubble is there, so this will be 0. This is 1, this is 0. Both are off. If both are off, then what will happen? Basically, this is the scene. Both are off. Oh, yeah, sorry. Both are off. So at the output, you can always assume some parasitics. These parasitics cap can come from anywhere. These capacitance can come from anywhere. It could be coming from the next stage, or it could be parasitic of this guy only, or this guy parasitic could be there. So at output, you can always assume some parasitic. Right? If I am assuming parasitics, that means this capacitor is open-ended now. This capacitor is open-ended. If this capacitor is open-ended, what does it mean? It is holding its previous value. If this capacitor is open-ended, that means it is holding its previous value. Whatever the value was there, it is holding its previous value. So what I will write, my F is, this is your F actually. Both are off. Basically both are off. So my F is high Z. We have used this term when we were studying tri-state buffer. I remember this, when we were studying tri-state buffer, we used this term high Z. That means high impedance. Okay, G stands for impedance. So this is high G state. And in high G state, what do you see? Hold operation. C is capacitor is holding its previous state. So hold operation is there. Okay. So this is your enable 0. Now if enable 1 is there, then what will happen? Let's see. This is enable 1. Enable 1 is there. So this is 1 and this is D. Here you are getting D bar. Enable 1. So this is 0. So D plus 0 will be D, and here also you are getting D bar. So what you will get at the output? D. Right? This is a simple inverter only, no? CMOS inverter it is. Simply an inverter. So at the output what you are going to get? D. So whatever the data that you are having, that is latched here. If enable is 1 and if enable was 0, it was doing the hold operation. So what do you think? What is this? D latch. So this you have implemented D latch. If enable is 0, it is holding the previous state. If enable is 1, F is equals to D. So this is your D latch. Okay. So whatever that you made here, that was D latch. So let's remove it off. Or I could have written here, this is your D, enable, and this is your enable, this is your D. So I could have written here enable into D bar, and this I could have written enable bar plus D, enable bar plus D bar. Okay, so I can write enable into D bar. Forget it yaar, itna simple hai, like it is very simple. Okay, let's solve the next question. This would be the last one. Tell the answer. Okay, solve it with good amount of patience. What will be the output expression? AB or AB bar? What will be the output expression? Okay, someone is calling at the door. I will pause the video. You solve it, then I will come. Yeah, so what is your answer? AND gate? No, AND gate is not the correct answer. Why is that so? Look, in all the logics that we studied in CMOS, previously in CMOS, here we studied a lot of logic. So here, both were doing the same thing. Basically, this was connected to ground and this was connected to VDD, right? Ground to VDD. Because the thing here is that if you treat this and this, you will get the same thing. Let me tell you, take the example. What do I mean by that? V naught is equals to, if I treat this, that means I know that if A is there or B is there, then my output will be low, then I need to put a bar. Or using this, what I will get? Plus. This I can use as A bar. This is my A bar. Dot, since they are in series, dot B bar. And then 1 will come, no? So A bar dot B bar. If 1 is coming, I am not going to put any bar. So this is what I am getting. From here I am getting A plus B bar. Or this also, this network is also there, no? So from this what I am getting? A bar dot B bar. And 1 is coming, so I am not going to put anything. So what is this? A plus B bar only. So both are same thing. So eventually I can write A plus B bar. Both were serving the same purpose, right? But in this case, what is happening? Both are serving the same purpose or not? No, they are not serving the same purpose. Here it is connected to BA, some potential. This is connected to VDD. So what Y will say? That if A is there, if A is 1, then B will come to output. Or if B is 1, then A will come to output. Or if A is not there, if A is 0 and B is 0, then VDD will come to output. So this is the complete expression. No? If A is there, B will come, or if B is there, A will come, or A is not there and B is not there. Basically, what is this? A bar dot B bar. And since VDD is coming, I am not going to put anything. So what do you get here? Y is equals to AB plus A bar B bar. So what you get? A XOR B. Yeah. So these kind of questions can come. Otherwise, you could have made that truth table as well. Let's try making that truth table. This as a method 2. If both are 0 0, both are 0 0, A is 0, B is 0, this will be off, this will also be off. If both are 0 0, they will turn on. If they turn on, this would be 1. Okay, 0 1, A is 0, B is 1, so this will be off. So from upper side nothing is coming. A is 0, B is 1, this is off. B is 1, A is 0, so this is on. This guy is on. B is 1, A is 0, so this guy is on. So if this guy is on, then what will happen? A will go there. Basically A will carry here. And what is A? A is 0. A is already ground and B is 1. This will go up. Now A is 1 and B is 0. A is 1 and B is 0. So this guy will again be open circuited. From this guy what will happen? A is 1, B is 0. So this will turn on, 0 will go here. Right? And if both here, what is the scene? A is 1 and B is 0. If B is 0, this will not turn. Both are 1. If both are 1, then what is the scene? A is 1 and B is 1. This will turn on and A will go here. This will also turn on and sorry, if this will turn on, B will go here. If this turns on, A will go here. Both are 1 only, so 1 will be there. Are you getting this point? If both are 1, they will be open circuited. Forget about them. If both are on, they will be open circuited. So from upper side, nothing is coming. Look at the lower side. A is 1, B is 1. So if A is 1, this will turn on. So B will travel here. What is B? B is 1 only. B is 1 and A is 1. So this will turn on. A will travel here. So what is A? A is 1 only. So what you are getting? This is your XNOR gate. That's it. So all kind of questions that can be asked in your examination that we have covered. So do not worry about this particular logic family topic. Just see one more lecture. In that lecture, we are going to study about the characteristics. There we will talk about fan in, fan out, propagation delay, power dissipation, figure of merit, noise margin, all kind of things we are going to talk about in the next lecture, and we will solve some problems. So from that lecture as well, there is very rare chance of questions coming. Whatever the question is coming, that will come from this 75 minutes of lecture only. Okay then. Still you should watch that next lecture, that will be of roughly around 1 hour. Okay then. Thank you very much.